Hi, welcome to the final exam screencast. This is going to be question 2, and my name is Kevin Reynolds. So kind of like normal, we're going to kind of jump into an overview of what we're going to be doing. So we're going to look at Dan the peptide. Secondly, we're going to look at peptide formation, so how we actually create Dan, what Dan is, all the parts of it. And then we're going to look at some things along the lines of restrictions and things like that, like restricted bonds. And then we're going to wrap up with phi and psi angles. So let's jump right in. So, to understand Dan, we're going to have to understand 3 different amino acids, those being aspartate, alanine, and asparagine. So, what a peptide is in a sense, a connection or a conglomeration of multiple peptides linked together, or multiple amino acids linked together to form this peptide. So what you'll notice is that in all of the amino acids you have an NH3 positive and a CO minus group. These are kind of the linking factors that are going to actually bring the peptide together based on the amino acids. So what ultimately happens is a link between this kind of carboxylic acid unprotonated and this amine positively charged is going to combine along with the same thing with the alanines and asparagines linking together. So we're going to have our N on one side and our C terminus on the other side. So what that's actually going to look like is going to be our molecule or our peptide Dan. So you'll notice that it's going to be in 3 parts, and as I mentioned just before, is we're going to have these kind of linking bonds between that carboxylic acid part and the amine part. Kind of what it forms together when you look at it, it ultimately forms this amide bond, which is the linking factor between the 2 and 3 amino acids. So looking at a couple of aspects, we can analyze a couple of things. As you can kind of see right in here, these red bonds or these red atoms are going to be what are called our alpha carbons. Now the other dots that you kind of see are the blue dots right in here and here, where the 2 blue dots are. What these ultimately are going to be our restricted bonds. So these are bonds that don't actually rotate out of formation. It's due to the amide bond that was formed when the peptide was formed itself. Next, we're going to dive into those phi-psi angles that I kind of mentioned earlier on in the overview. What these are 6 points that align across 2 alpha carbons. As you can kind of see, there's going to be a red version and a blue version. One of these is going to be reference to our phi angles, one of them to our psi angles. Our phi angles are actually going to be the blue ones, and our psi are going to be our red ones. So we're going to get into what those kind of look like in their own right outside of the peptide. So, looking back, we're going to take a view kind of down the peptide itself, and we're going to look at phi angles first. As I mentioned, it's going to be looking, in a sense, from an N terminus straight down the peptide, so you can kind of see how we have our other part of the amide bond, so our ketone part of the amide bond coming down off of it, and then it rotates itself around until you see the further back part of the actual peptide or of this bond. What this kind of does is it lets you see how this bond or this peptide is rotated out of its alignment. In this regard, this one has a 60-degree, roughly, phi angle. And at the same time, we can look at psi angles from a different perspective. We're going to look based off of a carbon, and we're going to look at these kind of nitrogen bonds and nitrogens that are within the actual molecule or the peptide. With this one, we can see kind of an opposite approach where we're going to have a negative 45-degree psi angle. One of the big techniques that kind of looks at these, if you kind of recollect, is going to be our CD spec. We can kind of see the different formations in peptides and molecules and things like that and analyze those little teeny changes that end up showing a difference within the peptide itself.